Hello, STOC 2022. I am Nathan Harms, and I will be talking about randomized communication and implicit graph representations. This is joint work with Sebastian and Viktor Zamaraev. I will begin by explaining implicit graph representations. Then I'll move on to its relation with communication complexity. I'll talk just a little about our results, and then I'll conclude with some questions and open problems. So implicit graph representations. So here we have a class F of graphs, and this is a set of graphs which is closed under isomorphism. And we write F sub M as the set of n vertex graphs in F, and every n vertex graph G in F we think of as having vertex set 1 to n. Okay, so now one way that we can get such a class of graphs is to define them implicitly. And by this, I mean that there is some abstract set X and some relation over pairs of things in X. And we get our graphs in F by choosing some number of points in X as our vertices. So we choose some n vertices out of X, and we put an edge between two vertices if they are related by R. So for example, we could have interval graphs, permutation graphs, dot product graphs, and so on. And these are often hereditary. So for example, interval graphs are hereditary, which means that they are closed under taking induced subgraphs. So for any graph G that comes from this set X and this relation R, if we take these subset of these vertices and we look at the graph induced on that subset, it also belongs to our class F. So for example, an induced subgraph of an interval graph is also an interval graph. So let's think about interval graphs a little more. Here we have our set X is the set of all pairs of real numbers, or rather the set of intervals between two real numbers, where R relates to intervals if they intersect. So to get the class of interval graphs, we take n points from this space. So we take n intervals, and we put an edge between two intervals if and only if they intersect. Okay, so for example, this graph G we get by taking 4 intervals from this space X, and they might look like this so that they have this star shape. Okay, so now a very nice property about this type of graph, these interval graphs, is that each vertex is just associated with an interval. So we could imagine that we take all of our vertices, or rather all of the intervals associated with the vertices, and we distribute them among a number of people. So let's say each vertex is a person. We can give that person just one interval, and then when the people go about and they meet each other, they can decide whether they were adjacent in the original graph G without having to talk to anybody else. They don't have to know anything about the rest of the graph G. They just need to know the 2 intervals that are associated with their 2 vertices, and they can decide whether they were adjacent in their original graph G. So this is some kind of distributed representation of these graphs. But there's a problem with this kind of representation, which is that these things are real numbers. We don't want to make these people store arbitrarily precise real numbers in order to represent their graph and decide adjacency. We want them to just store some hopefully small number of bits so that they can decide adjacency. Now for interval graphs, this is not too bad, because even though it's defined in terms of the real numbers, when we have some fixed graph G on only n vertices, there are only 2 n numbers that we actually care about. So each interval we only care about its beginning and ending number. There's only 2 n of these numbers, so we can replace each one of these numbers with just an integer from 1 to 2n. And then we can write these down using log n bits each, so that in total, we only need to use 2 log n bits to represent each interval. So we can imagine that now we give the intervals to all of the people, but now they only need 2 log n bits to write them down, and then they can go on their way. And when they meet each other, they can decide whether they were adjacent in the original graph G using only those 2 log n bits. Okay, so in general, what we want to do is we want to replace this arbitrary set X, this big set X with its relation R. We want to replace it with binary strings and a relation over those binary strings. So specifically for a hereditary class F, we want to find some relation D, which we'll call a decoder. We'll think about this as a decoding algorithm that takes as input 2 binary strings and outputs 0 or 1. And we want to define it in such a way that for every graph G in our class F, there exists a function which we will call a labeling, which assigns a binary string to every vertex in such a way that for every pair of vertices, X and Y, the decoder, when it is given the 2 labels of those vertices, it's going to output 1 if and only if X and Y were an edge in the graph. So our decoder can decide whether X and Y were adjacent using only the labels assigned to X and Y and nothing else about the graph G. So it doesn't know G. And now we want these representations to be efficient. So we need to define the size, and we just define this in the natural way. We say for any number n, the size is this function from n to the maximum size of a label given to a vertex in a graph on n vertices. Now, it turns out that every graph class has such a representation because for any vertex in any graph, we can always just give it the row, its own row in the adjacency matrix, as well as the name of the vertex itself. So that then when 2 people meet, they can use their vertices, their vertex names as the index into the row in the adjacency matrix and determine whether they were adjacent or not. But the size of this representation is linear in the number of vertices, which is not very good. We would like to get this as small as possible. There is a lower bound on how many bits we require for these labels, which comes from the total number of graphs in the class. So here we have the total number of n vertex graphs in the class. And since we can recover the graph from the set of all of its labels, so if we have all n labels of all the vertices, we can decide which ones were adjacent to each other, which means this is a encoding of the graph, which means that we need at least log of the number of graphs in the class in order to represent each graph. And that means that we need each label size, there needs to be the maximum label size needs to be at least 1 over n times this log of this number. Okay, so now the question is, when is this minimum achieved? For which classes can we achieve this minimum? And this is a question asked by Kanan, Nauer, and Rudich 92 and Muller 89. So in other words, when can an asymptotically optimal representation of the graph be distributed sort of among all of the vertices? And most work on this problem focuses on the special case where the labels are size order log n. So just a constant vector more than what's required to give unique labels to every vertex. And a necessary condition for this is that the number of graphs in the class is at most 2 to the power order n log n, so that this minimum size doesn't rule out these kind of labels. And this sort of representation of graph is called an adjacency labeling scheme. Now, there's another way to think about this, which is as a universal graphs or induced universal graphs. And so we think about this as replacing our set X and R with some finite object of as small as possible. And so this is called a universal graph, which is a sequence of graphs, U1 through UN, so that every graph G on n vertices in our class is an induced subgraph of UN. So we've taken our big space X and we've reduced it as small as possible to these universal graphs UN. So the class F is now implicitly defined as induced subgraphs of these universal graphs. And this is an equivalent problem to adjacency labeling because we can just define the vertices of our universal graph to be the set of all possible labels for graphs in the class with adjacency if and only if the decoder would output 1. Now, just for a concrete example, let's think about forests. So in a forest, 2 vertices are adjacent, X and Y are adjacent if and only if X is the parent of Y, or vice versa, when we give some arbitrary root to each tree in the forest. Okay, so the labeling scheme we can just write down for a vertex X its own name and the name of its parent. And from these labels, the decoder can determine if two vertices were adjacent just by checking if one was the parent of the other one. Okay, and so the universal graph for this looks like where the vertices of the universal graph are pairs of integers, where A, B, and C, D is an edge of the universal graph if A is equal to D or B is equal to C. So there's some universal graph of small size, polynomial size, in fact, where every forest is an induced subgraph of this universal graph. Okay, so now let's talk about communication complexity, and I'll introduce something called adjacency sketching. So communication problem is a sequence of functions. So f sub n is the communication problem on input size n. So we think of the inputs as being pairs of numbers from 1 to n. And here, just note that I'm using n as the domain size of the problem. And for this talk, our communication problems have Boolean values. So these are Boolean valued communication problems. And a communication protocol is where Alice receives an input X and Bob receives an input Y. And then they share a pool of random coins. So we're in the public coin communication model. So there's a set of random coins. They both see the same ones, and they use this to come up with a randomized communication protocol. So they see the random coins and then they communicate back and forth. And in the end, they want to output f of x, y correctly with probability at least 2/3. Okay, so they're allowed to make an error, but only with probability at most 1/3. And the cost is the total number of bits of communication that were used by the protocol. So now this is an equivalent to Alice and Bob computing adjacency of two vertices x, y in a bipartite graph. So we can think of Alice's inputs being on the left of the bipartite graph and Bob's inputs on the right. And we connect two vertices if f of x, y is 1. So if these two vertices correspond to a 1 input to the function f, we connect them in this bipartite graph. So communication problems are equivalent to adjacency in some bipartite graph. So a standard example of this is the equality function. The equality function on two inputs x and y is 1 if and only if x and y are equal. So in graph representation, equality is just computing adjacency in a matching. So now there's a very simple and very nice communication protocol for this that only uses 2 bits of communication. And here, Alice and Bob use their shared randomness to find a hash function of the numbers 1 to n. And they hash each number to just 2 random bits. Now, Alice just sends the hash of her vertex x, and then Bob outputs 1 if and only if the 2 hashes are equal. So if x equals y, then they will see the same hash function with probability 1 and output 1. And if they are not equal, then they will have a collision in the hash with probability at most 1/4. So this communication protocol will have an error with probability at most 1/4. Okay, so now let's introduce adjacency sketching by remembering the labeling scheme, adjacency labeling scheme for forests. So for a forest, remember that we gave each vertex a label, which was just its own name and the name of its parent. And the decoder just checked whether x was equal to the parent of y or y was equal to the parent of x. And so it's nice that this labeling scheme only checks equality of 2 different things. So what we can actually do is use the same idea as from the previous slide and just use our hashes. Instead of checking x versus the parent of y, we check the hash of x versus the hash of the parent of y and vice versa. So we only need to check equality of a couple of different hash codes. And then what happens is that we end up with a randomized label. So we can assign to every vertex a random label so that between 2 vertices, we can check if they were adjacent with probability at least 2/3 if we choose our hash function large enough, but still constant. So this is actually, we assign only a constant number of bits to each vertex. So in general, we are going to define adjacency sketching, which is the randomized version of adjacency labeling. So for a hereditary class F, we again want to find some decoder D such that for every graph in the class, there exists a random labeling, a random assignment of binary strings to each of the vertices, so that for any two vertices with probability at least 2/3 over the choice of these random labels, the decoder will correctly determine whether those two vertices were adjacent in the original graph, and it will do so without knowing the graph, only knowing the two labels. And once again, we define the size as the maximum size of a label given to an n vertex graph. And so the question that motivates this paper is that, well, forests have constant size adjacency sketches. What else has a constant size adjacency sketch? Which hereditary classes give us constant size adjacency sketches? And so just a note for those of you familiar with communication complexity, this is a generalization of simultaneous message passing, where here the referee does not know the specific instance of the problem that it's supposed to compute. It only knows the general class of the problem that it's supposed to compute. So it doesn't know the graph. And this means in particular that the trivial log n upper bound on the communication complexity no longer holds. Okay, so now we want to show that constant cost communication is equivalent to constant size adjacency sketches. So what I mean is that for any hereditary graph class with a constant size adjacency sketch, we get a communication, an associated communication problem with constant cost communication and vice versa. So one direction, this is easy. So if we take a hereditary graph class with a constant size adjacency sketch, all we do is we just define the adjacency problem for that class. And if it has a constant size adjacency sketch, then Alice and Bob can use their shared randomness to simulate that sketch. Alice sends the sketch of her vertex X to Bob, and Bob simulates the decoder and then outputs adjacency. In the other direction, we have a communication problem, and we want to construct a hereditary graph class with a constant size adjacency sketch. So a communication problem, there's only one problem of every size, or equivalently, there's only one bipartite graph of every size, and we want a hereditary class. So what we do is we say, well, we're going to take all of those bipartite graphs and we're going to take the hereditary closure. So the set of all induced subgraphs of these bipartite graphs, and we're going to put those in our class. Now we need to show that this has a constant size adjacency sketch. And how we're going to do this is we're just going to put all of the information into the sketch that we need in order to simulate the communication protocol. So for any class which has a constant cost communication protocol that computes adjacency, we can get a constant size sketch by associating with every vertex X a label which encodes all the information required to simulate the communication protocol. So we can write any communication protocol as a communication tree, so a binary tree which determines what Alice and Bob are going to do. And for every vertex, if it's Alice's vertex, we write down what Alice is going to do. And otherwise we write down what Bob is going to do. So for an input X, we write down on the left side here in this tree, we write down what Alice would do at every node in the tree, assuming that she has input X. And then on this part of the tree, in this second copy of the tree, we're going to write down what Bob would do if he was given vertex X. And then what the decoder can do, given the labels for X and Y, can take what Alice would do on input X and take what Bob would do on input Y and overlay those two trees together and simulate the tree from root to leaf. Okay, so since these communication trees were constant size, we only need a constant number of bits to put in this label so the decoder can simulate the communication protocol. Okay. So now another very nice fact is that using basic de-randomization techniques, we can actually go from a constant size adjacency sketch for a class F to an order log n adjacency label. So just using basic de-randomization, we can say if there's a constant size adjacency sketch, then there is an order log n size adjacency labeling scheme. Now this is interesting because the main open problem in adjacency labeling schemes is to determine which hereditary classes admit labeling schemes of size order log n. Okay, and that means that our problem here of which hereditary classes have constant size sketches, this is sort of the probabilistic version of that open problem. Okay, so we have this probabilistic version of which hereditary graph classes admit constant size adjacency sketches, and any such class must also admit order log n adjacency labels. Okay, so now I'm going to talk a little bit about the results from this paper, but I won't go into too much detail. So our goal with this paper was to study as diverse a set of graphs as we could and figure out what determines sketchability, what determines whether a constant size sketch exists. So I'm going to just talk very briefly about some of the results. So Cartesian products, minimal classes, and then quickly mention these other three interval and permutation graphs, H-free, bipartite graphs, and bounded twin width graphs. So Cartesian products, if we have any class F, which has a constant size adjacency sketch, we show that the hereditary closure of its Cartesian products also admits a constant size sketch. So what does that mean? Now, if we have any class F, we write F square for the set of all Cartesian products of graphs in that class. And then we write the closure of F square to be the set of all graphs, which are induced subgraphs of Cartesian products of F. And we show that if F has a constant size adjacency sketch, then this closure of the product does as well. Or in other words, the Cartesian product preserves the constant size adjacency sketch. Okay, now one reason that this is interesting is that then we get order log n adjacency labels for any such class by de-randomization. And so these labels are actually, were not previously known. So this shows that you can use upper bound techniques from communication complexity to get new results for labeling schemes. Now, another interesting observation here is that a standard technique for labeling schemes actually corresponds to constant cost deterministic communication with an equality oracle. So I mentioned equality is a standard example of constant cost randomized protocol, and we can imagine that we have an equality oracle instead, and a deterministic protocol, and this corresponds to a standard technique in labeling schemes, and we show actually that this technique cannot possibly recover these results here, these labeling schemes that we get from de-randomization. Now, just a few words about minimal classes and stability. So I mentioned that any class with order log n adjacency labels must have at most order 2 to the order n log n graphs in the class. And if they have asymptotically fewer, then these are very simple. So we are mainly concerned with the ones that have omega n log n graphs in the class. And it turns out that there are 9 minimal classes in this so-called factorial layer. So for a class to be non-trivial, essentially, it must contain at least one of these minimal classes, and 3 of these classes look like these ones as follows. So now these are very interesting because these are the graphs which correspond to the greater than communication problem. So now it's necessary that any class that is sketchable does not contain any of these minimal classes. And indeed, these are the only minimal classes with non-constant sketches. So out of the 9 minimal classes, these 3 are the only ones with non-constant sketch size. So now there's 2 necessary conditions for sketchability that we know. One is that the number of graphs in the class is bounded by this n log n function. And the second is that they're stable, which means that they do not contain these 3 minimal classes that correspond to the greater than communication problem. So now our goal is to study a diverse set of classes with that satisfy these conditions and see what else is necessary for constant size sketches. Now, the surprise is that for all of the classes that we studied, these 2 conditions are actually sufficient. So I already mentioned Cartesian products, but for interval and permutation graphs and H-free bipartite classes, and for classes of bounded twin width, we found that actually these 2 conditions were sufficient. Now, the main technique in these latter 3 results, at least, is to find a recursive decomposition of graphs in these classes where the depth of this decomposition is bounded by the size of the largest greater than problem. So if that size is bounded by a constant, then we get a constant size decomposition tree. So now just some notes on questions and open problems here. So due to the diversity of the examples that we studied and the surprising fact that stability and this factorial speed condition were sufficient, as well as some other reasons that we discussed in the paper, we actually conjectured that these two conditions were necessary and sufficient always. And we thought of this as the probabilistic version of the 30-year-old open problem in the field called the implicit graph conjecture, which stated that this factorial speed condition was both necessary and sufficient for these order log n labels. Now, it was very surprising to us, but our conjecture was disproved very fast after a preprint appeared online within, I think, 1 or 2 weeks by Hambardzumian, Hatami, and Hatami using an interesting proof barrier construction from their concurrent work on constant cost communication. And then very rapidly after that, Hatami and Hatami also refuted the implicit graph conjecture itself, which was very exciting. So now, as an open question, now this conjecture is false. So the question is, well, which hereditary classes admit order labeling schemes of optimal size, particularly order log n? And our probabilistic version, which hereditary classes admit constant size sketches? And I just want to mention one problem here is that this implicit graph conjecture, it's false, but we still have no techniques, not a single lower bound technique for proving super logarithmic lower bounds on a fixed class of graphs that satisfies this required condition here of order n log n speed. So there's not a single technique that we know where we can apply to prove a lower bound against a fixed class that we're interested in. So communication complexity, people really love lower bounds. So maybe there is some way to use some communication techniques to try and give the first lower bound technique for this problem. That would be really interesting. All right, that's it for this talk. Thank you very much.